Welcome to workshop number 6. This is the workshop for stereoisomerism. So let's hop right into it. For the first problem, let's look at some pairs of molecules, and we are going to determine the relationship between these two molecules. They can either be the exact same molecule, they could be enantiomers, diastereomers, or they could be two entirely different molecules. Okay, so let's use what we know about stereoisomerism to figure out this first set here. So this first set of molecules looks like we have a 1, 2, 3, 4, 5, 6 carbon chain, 6 carbon chain. On the third carbon of each chain, we have this wedged methyl group. Okay, we have that wedged methyl group. So it looks like they're not entirely different molecules. They could either be the same molecule or possibly enantiomers. We only have one stereocenter, so there's no possibility of diastereomers. Okay. So both of them are 6 carbon chains. Both have a methyl group on the third carbon. The methyl group is a wedge. So what we really should do here is figure out R or S configuration for each one. And if they're both R or both S, it means that we have exactly the same molecule. If one is R and one is S, then we have enantiomers, okay? So let's look at this first one here. The hydrogen is already in the back. Okay, remember you put your lowest priority group in the back. And then the other three groups labeled 1 through 3 based on their priority, we determine either R or S via the clockwise versus counterclockwise. Let's go ahead and put priorities on our groups just so we remember how to do that. Priority, remember, is based on the periodic table, our atomic number. Hydrogen is the lowest priority, so we're going to put that 4. And then all we have are carbon chains with single bonds in every direction. So our highest priority group will be the longest carbon chain because it has the most carbons on it. And then the next would be the 2 carbon chain. And then the 1 carbon chain would be priority 3. So going 1, 2, 3 with the 4th group, the lowest priority group in the back, this would be counterclockwise, which is of S configuration. And now some of you may have looked at these two molecules and seen that they are pretty much the same thing, just drawn at a little bit different angle, and determined that they were exactly the same molecule. That's perfectly fine. But let's go ahead and check and see if this is also S configuration over here. Hydrogen is our lowest priority group. Our longest carbon chain is 1, and then 2, and then 3 for the methyl group. These are going in a counterclockwise fashion, S stereocenter. So both of these are S stereocenters, 6 carbon chains, methyl group on the third carbon. These are the same molecules. Now, like I was saying, some of you may have seen that we have this downward angle shape between these 2 carbons and then a wedge. Over here, we have a downward angle shape here and a wedge. That's another little technique you can use to see if you have the same molecule or not. Just look at how they're drawn and try to rotate those bonds and move the molecule around in 3 dimensions to line up the 2 molecules and see if they are, in fact, exactly the same. But if you're not comfortable doing that, a good, reliable way is to do what we just did here. Put priorities on your groups and figure out what that stereocenter is, whether it's R or S, and then compare it to the other one. Okay. I'm going to draw a few more sets of molecules here. What about this set here? If we have a 1, 2, 3, 4, 5 carbon chain with an alcohol, and then we have 5 carbon chain with an alcohol over here. Okay, so in both cases, it's a 5 carbon chain, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. And in both cases, the alcohol is on the second carbon. Remember, you count from the side which is closest to those functional groups. So you can start from the left over here, start from the right over here. In both cases, the alcohol is on the second carbon of the chain. Now, One thing you could do is what we just did. You could determine R or S configuration because we know we have 5 carbon chains with an alcohol on the second carbon. So they're both the same so far. And you can determine R or S like we just did, or you can try to rotate the molecule, flip it, make them look the same, and then simply compare them and see if they are exactly the same. If you wanted to do that approach for this one, take one of the molecules. I'm going to take this one on the right, and I'm going to envision putting a spatula underneath it and flipping it over like a pancake. Flip it over. This alcohol that's coming out towards us here is going to be going into the page. And if we flip it over, it's going to be closer to this side. Let's flip that molecule over. And we get that. Okay. Now that's a good skill. That's something that I think is a really good skill, being able to flip molecules and rotate them, because just doing that, you can clearly see that these two are the same molecules. They look exactly the same, okay? Just by flipping this molecule over like a pancake. So that's a really great way to do it. If you can do that, that's great. If you're not comfortable rotating the molecules and you want to determine R or S configuration, let's do that as well. So in this case over here, we have a hydrogen. It's a wedge. Now we need to put priorities on our groups. The hydrogen is the lowest priority. The oxygen is going to be the highest priority. And then we have a longer carbon chain, and then we have a shorter carbon chain here. 1, 2, 3, 4. Okay. Now we need to put the lowest priority group in the back. Okay. So we can do that several different ways. What I like to do in this situation is simply determine the rotation. This is 1, 2, 3 clockwise, and then simply flip it. Okay, that's one thing you could do. The other way you could do this is by flipping the molecule, put a spatula underneath it, flip it so the hydrogen is truly in the back, and then determine R or S. But this is the little shortcut I like to do. We already have the hydrogen in the front. Groups 1, 2, and 3 are going clockwise, which would be R. But since the hydrogen's in the front, then you flip it. So it's not R, but S. Okay. So instead of putting this lowest priority group in the back, you can simply put it in the front, determine R or S, and then flip it. So if you got R, then it becomes S. If you got S, it becomes R. That's another way you can do it without having to rotate or flip the molecule. Alternatively, once you label your groups 1 through 4, you can simply flip the molecule to put the hydrogen in the back and then count 1, 2, 3, determine R or S. Either way is perfectly fine. So this one is S over here. This one's nice because the hydrogen is already in the back. That's group 4. And then looking at our other groups, 1, 2, and 3, we see that we have counterclockwise, which is S. So again, these are the same molecules, just drawn differently, just drawn from a different perspective. Okay. Okay, what if we had this molecule here, OH versus essentially the same molecule, but we have OH as a wedge. So here is quite simple because the carbon skeletons are fully aligned with each other. The alcohols are clearly on the third carbon in both cases. In one case, we have a wedge, and in one case, we have a hash. So all of the stereocenters are flipped. The carbon skeletons are the same, and the stereocenters are flipped. So these would be enantiomers. Let's check using our R or S configuration. Okay, in this case over here on the left, we have a wedged hydrogen. That's going to be our fourth priority. Our oxygen is top priority 1. Our longer carbon chain is 2, and our shorter carbon chain is 3. Hydrogen is in the front, so let's take our measurement and then flip it. 1, 2, 3, as shown, is counterclockwise, which is S, and then we're going to flip it to R, since that lowest priority group is in front, but it should be in back. So this is R. Over here on the right, the hydrogen is in the back, which is our lowest priority. And then our other groups, 1, 2, and 3, are going counterclockwise, which is S configuration. So we have the R stereoisomer and we have the S stereoisomer. So these are enantiomers. Okay, remember enantiomers, every single stereocenter is flipped. If you just have one, that's fine. That means that one stereocenter is flipped. If you have 10 stereocenters, it means all 10 stereocenters are flipped. What if we have this 5-membered ring? Chlorine and a methyl group on it. And then over here we have this. Okay, so what are these two molecules? What's the relationship between these two molecules? So we have a 5-membered ring, we have a methyl group, and we have a chlorine in the same positions. The only difference is their stereochemistry. On the left, the methyl group here is a hash, the chlorine is a wedge. Looking at the right, the methyl group is a hash, and the chlorine is a hash. So they're not enantiomers, because for enantiomers, every single stereocenter has to be flipped. But for diastereomers, only a fraction of the stereocenters are changed. And in this case, only a fraction of the stereocenters have changed. So these are diastereomers. These are diastereomers. Remember, for that to work, your carbon skeleton needs to be perfectly aligned. Okay? Your carbon skeleton has to stay the same. And in this case, our carbon skeletons are the same. So we can simply look right at those stereocenters and determine if they're flipped or if they're the same. In this case, the methyl group stays exactly the same, but the chlorine changes, starts as a wedge, goes to a hash. So one of the two stereocenters changed. These are diastereomers of each other. Okay, and then for the final one, what is the relationship between these two molecules? So we have 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6 carbon chains. We have a double bond on the second carbon in both cases. Okay, double bond on the second, going from the second to the third carbon. In one case, we have a trans double bond, meaning the functional groups are on opposite sides of this double bond. And on the right here, we have a cis double bond. Those two groups coming off that double bond, that di-substituted double bond, are on the same side, right? Trans double bond versus a cis double bond. Now, I didn't touch too much on double bonds in the lectures because they don't come up all that much. Typically, when we discuss stereochemistry, it's the stereochemistry of a chiral carbon, but double bond stereochemistry is quite simple. When you have a trans double bond, you have a cis double bond. These are simply diastereomers of each other, because we have to remember the definition of diastereomers and enantiomers. Remember, for diastereomers, they are not superimposable and not mirror images of each other. They are not mirror images, they are not superimposable, but they have the same structure and they have the same connectivity, so they're stereoisomers, but they are not mirror images and they're not superimposable. So double bond isomers are diastereomers. Okay? Double bond isomers, trans, cis, these are diastereomers. They are not superimposable, not mirror images. So for the next question, let's look at these three molecules where I did not draw any stereo definition, and let's determine how many possible stereoisomers we have for each of these molecules. How many different stereoisomers are possible? Okay, so what we have to do is we have to figure out how many stereocenters we have, right? If we have to figure out how many stereocenters, how many stereoisomers are possible, we need to find out how many stereocenters we have. So looking at this first molecule on the left, let's count up our stereocenters by putting red dots on them. This second carbon in the chain is connected to 4 unique groups, right? It has an oxygen, a methyl group, it has this long chain over here, and then it has a hydrogen. So that second carbon in the chain is a chiral carbon. The central carbon is also chiral. It's connected to 4 unique groups, oxygen, a hydrogen, and then 2 different carbon chains. And then this carbon is also a chiral center, giving us 3 chiral centers on that molecule. Remember the possible stereoisomers we can get from the equation 2 raised to the n, where n is the number of stereoisomers. So if we took this first one, this would be 2 raised to the 3rd power, since we have 3 stereocenters, which would give us a total of 8 stereoisomers. Okay. I'll draw 1 or 2 of them up in the top, just so we have an idea of what that looks like. So one stereoisomer we could have is when these are all hashes. There's one stereoisomer. Another stereoisomer, the enantiomer, would be if they were all wedges. And then we have 6 diastereomers, which we could draw by interchanging the hashes and the wedges to create different combinations. Okay, so we have these 2 enantiomers, and then we have 6 diastereomers. Okay, so a total of 8 stereoisomers if we have 3 stereocenters. What about the last one? I drew a slightly more complicated molecule. Maybe it's a good idea to pause the video and think here. Try to figure out exactly how many chiral centers we have on this molecule. Okay, so I'm going to fill in with red all of the chiral centers we have. These are carbons connected to 4 unique groups. And it looks like we have a total of 4. 1, 2, 3, 4. All 4 of those carbons are connected to 4 unique groups. 2 raised to the 4 would be our total possible stereoisomers, which would be 16. So for the next problem here, what we have to do is determine R or S configuration using the Kohn-Ingold pre-log system, and then we will draw the enantiomer. Okay, so here we have one chiral center. You may be thinking this is a chiral center here also, but this carbon in question that I bolded is actually connected to 2 of the same group, CH2, 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 CH2. So that is actually not a chiral center. We just have the one chiral center here with the chlorine on it. Okay, that's the only carbon connected to 4 unique groups. So let's determine R or S configuration here. Our chlorine is our highest priority group, and the hydrogen in the back will be the lowest priority group. We have 2 carbon chains otherwise. Let's work down the carbon chains. In the blue direction, we have a carbon connected to 2 other carbons and 1 hydrogen. Going off onto the left, let's do green here. This carbon is a CH2. It's connected to one other carbon and then two hydrogens. So our blue chain over here is going to be higher priority because it's connected to two carbons instead of just one. Okay, so let's put this chain over here as 2, this chain over here as 3. Our lowest priority group is in the back, so we simply go 1, 2, 3, which is clockwise. This is our configuration. So let's draw the S enantiomer over here. Remember, to draw the enantiomer, the easiest way I think is to draw the exact same carbon skeleton and simply change the wedges to hashes and the hashes to wedges, and this is the S enantiomer. Okay, I think that's probably the easiest way to do it, but if you wanted to draw the mirror image, you are perfectly fine to do that as well. What would that look like? If you wanted to draw the mirror image, chlorine, you could draw it from any angle. I'm going to draw the mirror image here. We do this, this. We have a wedged chlorine here. Then we have the 6-carbon ring over here. So this would be the S enantiomer, and this is perfectly acceptable as an answer as well. If you wanted the molecules to look the same, then you could flip this molecule over, and if you flipped it over, this chlorine would be a hash instead of a wedge, right? Because it's coming out at us as a wedge here. If we flipped it, it would be a hash. It would be going away from us, but it would look more like this. Okay, so either way that you want to draw the enantiomer is perfectly fine as long as you do it properly. Either draw the mirror image or draw the carbon skeleton exactly as is and change all the hashes to wedges and all the wedges to hashes. Okay, for the next problem here, this one is a classic. I always love doing this problem, and sometimes I'll even put more examples on the board. But what we're doing in this problem is we're simply determining if we have R-limonene or S-limonene. Now, limonene is the molecule that's shown, and we can either have the R configuration or we can have the S configuration. Now, we can visualize it. We can draw limonene, both the R and the S, in many different ways. So it's up to us to determine, based on how each one is drawn, whether it's R or S. Okay, so obviously the most reliable way to do this would be using the Kahn-Ingold prelog system to simply determine R or S at the stereocenter in question. But I think it's also an excellent exercise in visualizing the molecule, flipping it around, rotating it, and getting a better understanding for how to do all that. Okay. So let's look at the very first problem here, and let's simply use the Kahn-Ingold prelog system to determine whether this is R or S. So we have the hydrogen here, which is the implicit hydrogen. Let's draw that in as a wedge. And now we have 3 different carbon groups. So this hydrogen is going to be priority 4, obviously. And then all the other carbons we have to figure out, 1 through 3. So let's go off in each direction. Going in the red direction here, we have a carbon connected to 2 other carbons and 1 hydrogen. Going off in the blue direction, we have a carbon connected to a carbon and 2 hydrogens. And going off in the green direction, we also have a carbon connected to 2 hydrogens, another carbon and 2 hydrogens. So the red chain is going to be priority 1, our highest priority. And now we have to determine between blue and green what priority 2 and 3 are. So going down the blue chain here, we have, again, CH, a carbon connected to one carbon and two hydrogens. Going down the green chain, we have a carbon connected to two carbons. It's double bonded, and it has one hydrogen. So the green chain actually gets an additional carbon first. So the green chain is going to be prioritized higher above the blue chain. So let's give this green chain here priority 2. And then the blue chain up top, priority 3. Okay, I'm going to erase this extra stuff now that we don't need it. Okay, so we have our priorities 1, 2, 3, 4. Now I'm going to do the trick that I like to do. Since our hydrogen is in front, I am simply going to take R or S and then flip it. So going 1, 2, 3, like this, is clockwise, which is R. But since the hydrogen is in the front and it should be in the back, I am going to flip it and it's going to be S. Okay, so this first one here is S priority. This is S limonene. And we figured that out by using the Coningal prelog system, determining our priority groups, determining R or S, and arriving at our answer. Okay, so we can do that again, or what we can do for practice is look at the other molecules here and determine if they are exactly the same by flipping it so that it lines up with this molecule, or if it's the enantiomer R. So let's look at the one in the top right here first, the one I just boxed in. Now, if we want to line up this molecule in the top right with the molecule here that we've already solved, S, all we have to do is we have to take this molecule and we have to turn it. We're not going to flip it or anything. We're going to take this molecule in the top right. We're going to envision grabbing the left side of it, grabbing the right side of it, and simply turning it. Like if you took a pizza on a countertop and you just grab both sides and you just spin it, you just turn it. If we turn this molecule, leaving it as is, but just turn it 180 degrees, then it's going to look exactly like the molecule here on the left. Let's draw what it would look like. So we turn that molecule 180 degrees. So we're not changing anything about it. We're just redrawing it. And we can see we have a wedge in this position instead of a hash. So that means this is the R configuration, the opposite configuration, the enantiomer. So this one up here is R. The other way you could solve it is exactly as we did the first problem. Prioritize your groups and then simply count 1, 2, 3, and it should give you a clockwise configuration around that chiral center. If you put that hydrogen in the back, which it already is conveniently, 1, 2, 3, that would be our configuration. I'm going to keep using, for the last two, practice in flipping the molecules because I think it's important. But if you want to continue using R or S, that's perfectly fine as well. So how do we get this molecule here that I just circled to line up with either one of these two? We have S and R. Let's try to line these up. Now, let's just line it up with S since we've already done that. So let's take this molecule that I circled here and let's match it up, the carbon skeleton, match it up with S, and then we can simply look and see if we have a wedge or a hash. So to do that, it looks like what we need to do is we need to take this molecule. I'm going to draw a handle on it because, you know, I like to make this reference of flipping things. So envision flipping this molecule in the circle, flip it like a pancake, put a spatula underneath it, and flip it. If you were to flip it, hopefully you can see how it would look just like it does up here. where I have the S, right? It should look just like that if we flip that molecule. So envision putting a spatula under this molecule, flipping it upright, right? Flipping it up towards S, and that would give us this molecule here. That would be there. And if this group that I circled, see this group here, it's coming out at us. If we flipped the molecule, it would be going away from us down here, like that. So this is exactly the same as this first one we did. This is the S configuration, right? It's exactly the same. The carbon skeletons are exactly the same, and we have a hash in this position instead of a wedge. So this is S-limonene. And again, you could use the Con-Angle pre-log system for this one, number 1 through 4, and then determine R or S. That's perfectly fine as well. And now for the very last one, how do we get this one to line up? Well, this one is already lined up, right? This very last one here is already lined up with the first one we did. And you can clearly see the only difference is the wedge versus the hash. So this is clearly going to be R-limonene because it's the opposite configuration as this S. We have a wedge instead of a hash, and the carbon skeletons are all lined up. Okay. So for this question, what we have to do is draw the enantiomer and then both diastereomers. So we have two stereocenters. 2 raised to the 2 power is 4. So we have 4 possible stereoisomers. We're shown 1. We are going to draw the enantiomer, and then we have 2 diastereomers that we have to draw. Okay. So I'm going to draw this in bond line structure. So if we have a 6-membered ring, we have a chlorine in the up position. And then just next door, we have a methyl in the up position, right? Methyl in the up position. This is the molecule we're given. How do we draw the enantiomer for this molecule? Well, we simply flip all the wedges to hashes and all the hashes to wedges. Alternatively, you could draw the mirror image. Okay, you could draw the mirror image. I'm going to draw the enantiomer simply by changing hashes to wedges. Chlorine, methyl. And then for the diastereomers, remember you change a fraction of the stereocenters, but not all of them. If you change all of them, that's the enantiomer. If you change a fraction, those are the diastereomers. So to draw the diastereomers, keep the carbon skeleton the same, remember, and just change one of the stereocenters, but leave the other. Methyl. And then do the opposite for the other diastereomer. And there's our 2 diastereomers we could draw. Okay, here's the enantiomer, and here are the diastereomers. Okay, so again, remember, if you're going to simply change hashes to wedges and wedges to hashes, make sure your carbon skeleton stays the same. It's very important. Alternatively, for the enantiomer, you could just draw a mirror image. Okay. What if we have this molecule here? Same question, different molecule. What if we have a OH and a methyl? Both hashes. Let's draw the enantiomer. The enantiomer of this molecule would be simply converting them both to wedges. OH methyl. And the diastereomers, we're going to simply change one of the 2 groups. So let's keep the oxygen the same change the methyl to a wedge, and then do the opposite. Okay, and there's the two diastereomers. Very simple once you understand the gist of things. The enantiomer, just change every single stereocenter, and for the diastereomers, you just change a fraction. So in the first case, I'm just changing the methyl group, and on the second one, I'm just changing the alcohol. Okay, and again, we have two stereocenters on this molecule, 2 raised to the 2, 2 raised to the n, that's 2 raised to the 2, 4 possible stereoisomers. We can have a pair of enantiomers and then 2 diastereomers. Okay, if we had 3 or more stereocenters, we would have more diastereomers that we could draw. Okay, and for the final problem of this workshop, a couple parts to this problem. Just wanted to touch on EE and enantiomeric excess and make sure we understand the optical rotation of enantiomers. So for this question, let's say we have a solution, and that solution contains 2 enantiomers, enantiomer A and B. The solution is 98% A and 2% B. What is the EE, the enantiomeric excess of the solution? Remember, the EE is the enantiomeric excess. It's the excess you have of one enantiomer over the other. So this is a very simple problem to solve. It's simply 98 minus 2, giving us 96%, because we have 96% more of enantiomer A than B. So this is a solution with 96% EE, an enantiomeric excess of 96%. Okay, so it's very simple if you have the percentages. All you simply do is subtract them to find the difference. Now for the second problem, if we have a solution and we're given that pure A has a specific rotation of 13.1, positive 13.1, and pure B has a specific rotation of negative 13.1, what is the EE of a solution with a specific rotation of plus 3.7? So the way that we solve this, remember, is we take the absolute value of the measured amount, which is 3.7, and we divide it by the overall, by the pure specific rotation, which would be 13.1. And we multiply this value by 100%, and that's going to give us our EE. So if we take 3.7 divided by 13.1, multiply that by 100, then we have about a 28% EE. 28% EE. And which enantiomer do we have more of, A or B? We have more of the A because the A is positive, and we're at positive 3.7. If we had equal parts, right, if we had 50, 50, A and B, the specific rotation would be 0. Remember, this is called a racemic mixture when you have equal parts A and B. When you have equal parts of both enantiomers, that's called a racemic mixture. We have 0% EE, and there's no optical rotation, right? One enantiomer should rotate plane polarized light in the positive direction. One should rotate it in the negative direction. So if you have equal parts, they cancel each other out, and you have no optical rotation. Okay, I think that's the most basic and best way to understand EE and optical rotation. Okay, so if you can understand this problem, I think that's plenty. Okay, that's all the questions I have for this workshop, stereoisomerism. The next lecture will be chemical reactivity and mechanisms.